So our next topic that we're looking at is something called the fundamental theorem of algebra. Now, we've already alluded to this. If we know that the degree of a polynomial function, is given whatever number, so we might have a second or third or fourth degree, then that also predicts the number of zeros that we're supposed to have. So far in the problems that we've looked at, if we have something like example 1, we have a second degree equation, a quadratic, and we have a highest exponent of 2, and so we expect to see 2 roots, and we do. We have a single root at x equals -1 and a single root at x equals +5 from our 2 factors. Same thing with example 2. Now we also have, the expected roots on there. So we have our single root happening at -1, excuse me, a double root because it bounces, a single root happening at 0, and a single root happening at +2. So our these are single roots, and this one gives us a double. But we still have all 4 roots, all 4 expected roots accounted for in some way from the graph. But what happens if that is not the case? What happens if we graph it and we don't see the number of roots that we expect to from our degree? So let's look at a couple examples. And again, we're actually going to be spending a couple days on the fundamental theorem. So I want to give you a preview of what the graphs are going to look at, but today we're really just going to be focusing on writing out these equations, and then we'll bring it all together in our next lesson. So here we go. Example 3, we have our function, he's a cubic, highest exponent is 3. So let's pop over to Desmos and sketch it out. So over to Desmos. So we've got our function, f of x, hit the keyboard. So f of x, or y equals, and then we have x cubed. Again, I'm hitting the little a with the b exponent to get to that cube if you're using the keyboard screen like I am. And then minus 3x squared. And then plus 4x. And minus 12. So I keep looking up, I have that on my other computer screen right now. Wait a second. We have a cubic, we would expect 3 intercepts. Oh, there's my kind of wiggle through the graph that I would expect, but it's still only hitting in one place. And specifically that one place, and this is why I like Desmos, it's hitting at about 3.6. So where'd the other expression go? Let's go back to our item. So let's do new share. There we go. So it goes through at about, where is it? 3.6. So at about 3.6 around here, we had a wiggle somewhere down here and then it went that way. So we expected 3 zeros because it's a 3rd degree. But really we only got 1. So that means our other 2 zeros are actually going to be complex zeros. Kind of like when we were working with quadratics, if we graphed that quadratic, we graphed that parabola, and it didn't hit the x-axis, we knew we had 2 complex zeros, and last time when we came across that, we'd use quadratic formula to find those. Okay, what about example 4? So same thing, x to the 4th plus 4. Now, I'm going to cheat a little bit. I would expect, just looking at the degree, I would expect 4 zeros because degree equals 4. But if I graph this out and test this out on Desmos, what's really going to happen is I'm going to have kind of a parabola looking thing up at 4. It just got pushed up 4 units. So in this case, no x-intercepts means I have no real zeros whatsoever. So somehow I need to be able to account for 4 complex zeros on this one. And so that's our fundamental theorem of algebra, kind of expanded to include all of our solutions. So our fundamental theorem of algebra really states the total number of complex zeros of a polynomial function equals its degree. So if I have a 5th degree equation, I'm going to have 5 complex roots. Now, don't forget your complex numbers. When we were talking about these last unit, they include both a real part and an imaginary part. So it's the same type of thing When I say I have 5 roots, well, some of them might be real and some of them might be imaginary or complex. The biggest thing too, when we were solving with quadratic formula, we had that plus minus piece in there. And when we looked at those, technically we called those kind of the opposite signs. Well, when we're specifically looking at complex numbers, we call them conjugates. So we call these conjugate pairs. So when we solved out for complex values in our quadratics unit, we'd have something like 3 plus I and 3 minus I. Those are our conjugates where all we're doing is flipping that sign. And so let's see how we might arrive at some of these algebraically, just so you can see where these answers are coming from. But then we'll focus the rest of our time on writing these equations, and then we'll come back on actually solving more of these out and doing more of the algebra practice next lesson. Okay, so pretty straightforward ones. And this is just going to use math that we've already used before. So our first function, f of x equals x squared plus 9. Well, this is just a quadratic. And so when we solve this out, one of the ways that we could do this is set it equal to 0. And then use one of our methods. We could use, well, we can't use graphing. They're complex zeros, so they're not going to show up on the x-axis. We could use factoring, but we don't have any factors that are sum of squares. So let's just go brute force. We have a single x term. Let's just get it x by itself. So subtract your 9 from both sides. And then to get the x by itself completely, we have to get rid of the square root, which means, or the square, which means we take the square root on both sides. When you take the square root, how many answers do you get? We get our positive negative. But because we're dealing with the square root of -9, how did we deal with the square root of negative numbers before? Now that's where our I came in. Now 9 is a perfect square. His square root is a 3. Square root of the negative, or technically -1, would give us the I, and then we have our plus minus. And so there's our 2 roots. They just happen to be imaginary numbers. So they fit in with, we have a total of 2 complex roots. They just happen to both be imaginary. So example 5. Again, I have a feeling if I was to graph this out, it would not have nice values on there, but I can't go brute force like I did before. I have multiple x terms. So what was the other method that always worked no matter what? And we could do completing the square, but with that 3 in there, it's not going to give us nice values. So let's just do quadratic formula. So x equals our -b plus or minus square root b squared minus 4 times our a times our c all over 2 times our a, which is 1. And then we simplify it out. So we still have our -3 out front. 3 squared gives me a 9. -4 times 1 times 4 gives me a -16, which means I'm really looking at -3 plus or minus the square root of -7. And unfortunately, I can't simplify the 7, but I can do the square root of the negative. So this is really -3 plus or minus I root 7 over 2. And technically, those are conjugates. We have that change of sign, the plus and minus. So we could apply these to solving these out. We're going to look at some slightly more complicated versions where we can bring in other solving techniques that we've used before. But today, let's focus the rest of our time on writing these equations, because if you know how the equations are written in the first place, going back through and solving using our different methods, that's going to come together a lot better. So if we know that every single complex zero is always going to happen as a conjugate pair, take that into consideration when you're given your list of possible roots when we're writing those out. Here we go. So this is basically letting us bridge the gap between factored form and standard form. Now, in lesson 6.1, I mentioned standard form from here on out is always going to have real, or technically integer, coefficients. So no fractions. That also means no complex numbers. So I am still going to write my function in factored form, but then I'm going to have to multiply everything out to actually write it as standard form with all integer coefficients in there. So first example, number 6, our zeros are 3 and 2i. Well, 3 is a real number. I don't have to do anything fancy with that. So when I write that part out, I'm just going to write x minus 3. Because again, don't forget, in your factored form, you're always subtracting your root. So then we have this 2i. Well, here's the problem. We can't just put 2i in there. If I multiply that out, well, my final answer, my standard form that's all multiplied out, is going to have i's as the coefficient. So I need my conjugate pair to make this work. So I also need to use negative 2i. All I'm doing is flipping the sign. So that means my two roots, I'm going to have x minus the 2i, and then I'll have x minus the negative 2i, which doesn't look that pretty. So let's rewrite that. So x minus 3 and x minus 2i and x plus 2i. Okay, so I'm supposed to write this in standard form. I need to multiply everything out. And then going back to kind of reminder of standard form, again, we have these weird exponents in there, but that just means we're kind of reducing down our numbers. So if we had an exponent of 4 to start, and the next one would be 3, then 2, then 1, we're going down in order. That's why we have the n minus 1, the n minus 2 in there. So let's multiply these out, and it's going to be a whole lot easier if we multiply out these complex parts first. If you think back to our quadratics, our second quadratics unit, when we did this with conjugates, we had some really nice things happen. So let's see what happens. So distribute out your first x. We're looking at x squared plus 2xi. And again, the order you write these in doesn't really matter as long as you're consistent through the whole problem. It'll help you see your matching terms. Then distribute out our negative 2i, so negative 2xi, and then minus 4i squared. I'm going to go ahead and copy down the x minus 3 so I don't forget about them. But I still want to simplify out things on the right-hand side before I go any further, because again, that's kind of messy. So I'm noticing that I actually have opposite terms in the middle. Those simplify out totally. And thinking back to what we knew about our I as in raised to different exponents, what does an I squared actually simplify out to? Oh, I squared is the same thing as negative 1. And negative 1 times negative 4, well, that would make a positive 4. And so then the only thing we're left with in that second expression is x squared and plus 4. No more complex numbers. That's the beauty of having to use a conjugate. Everything is going to cancel out in the end. So now I just need to multiply through with that x minus 3. So again, distribute out your x. We'll get an x cubed plus 4x, and then the negative 3 minus 3x squared minus 12. And then I'm going to write it in standard form, which means descending exponents. So x cubed minus 3x squared plus 4x minus 12. And there is our final function with all integer coefficients. Let's do that again with number 7. So our zeros are 4 and negative 4i, which means what does our conjugate need to be? Positive 4i. So again, I'm going to have a third degree equation. So in the end, I should end up with a highest exponent of 3. So our function, x minus 8, x minus a negative 4i, and x minus 4i. So I skipped a step on there. As long as you're careful and you still see that you have kind of those conjugate factors, then you're still good to go. Okay, multiplying out the second two factors, the x plus 4i and x minus 4i, we get an x squared minus 4xi plus 4xi minus 16i squared. But again, our xi terms in the middle completely simplify out. Our negative 16i squared, well, I squared is the same thing as negative 1. So that simplifies out to x squared plus 16, no more complex numbers. Distribute out your x plus 8. So we have an x cubed plus 16x minus 8x squared minus 8 times 16, 128. And so we want to rearrange to be in standard form. So x cubed minus 8x squared plus 16x minus 128. This is why when we started looking at graphed forms, I had to put some coefficients, some a values of fractions in there, because when we start having things like minus 128 and we start getting larger coefficients, again, our graphs are going to be either stretched out or pushed way up top, and it'll be hard to see them on a regular graph without that fractional a value. Okay, number 8. Zeros are -7 and -5i. So again, that means our conjugate would be 5i. Go ahead, pause the video and try this one on your own, then come back, see how you did. All right, so our function, x minus a -7, aka x plus 7, x minus a -5i, and x plus, minus 5i. So multiplying out the complex factors, x squared minus 5xi plus 5xi minus 25i squared, which simplifies out to x squared plus 25. Distributing out, we have an x cubed plus 25x plus 7x squared plus 7 times 25, large number 175. And then rewriting in descending order to have our perfect standard form, just flip-flopping our x and our x squared terms. And there is our function. Alrighty, number 9 looks a little trickier, but there's really only one extra thing we need to multiply in. So technically, what's our degree on this one? Now, if we have the positive 2i, we also need to use negative 2i. So we're going to have 4 factors on here. However, our first factor is 0. X minus 0 just gives us a plain x. Well, that's easier to deal with. We just multiply an extra x in at some point. Our root of 2, x minus 2. 2i, x minus 2i, and negative 2i, so x minus a negative or plus 2i. And again, let's kind of do this in groups. I can very easily distribute the x over the x minus 2, so that would give me an x squared minus 2x. Done. So now let's deal with the complex parts. Again, distributing out, we're going to get a plus 2xi and a minus 2xi minus 4i squared. But that simplifies out. Middle terms cancel, and the last term turns into a plus 4. Now distribute. So distributing the x squared, I get x to the 4 plus 4x squared. And then the negative 2x, so negative 2x cubed minus 8x. And then rewrite, so everything's in descending order with your exponents. So x to the 4 minus 2x cubed plus 4x squared minus 8x. So this one doesn't have a constant term at the end, but that's okay. And there is our function. Alrighty, as always, we need to keep in mind all of our previous ideas. They all kind of come together and play with the same overall kind of image of what's going on with these graphs. So as a review, we're going to write this with some multiplicity problems, and then we'll keep that in mind when we're solving out next lesson. So number 10, we have 3 zeros. We have a multiplicity of 1 for x equals negative 2. Wait a second, take this back to quadratics. If I have a solution coming out as negative 1/2, and if I'm going to want to do this in factored form and get it as close to that perfect standard form as I want, I don't want any fractions in there. So let's clear out that fraction, multiply both sides by 2. And then we can move the 1 over by adding 1. So one of our factors is going to be 2x plus 1. We're not going to have to do too much with that 0 factor, but the 3/2 factor, we want to do the same thing. Multiply both sides by 2. And then subtract a 3. So there's our other factor. And so these examples, they're just saying to write it in factored form, so I don't have to get fancy with it. I don't have to multiply these all the way out. So I've got my negative 1/2 factor had a multiplicity of 2. So that means I've got 2 of these 2x plus 1s. Next one is a 0, literally 0. with a multiplicity of 2. So that's just x minus 0, or just a plain old x squared. And again, I could put that out front, or I can leave it where it is. Doesn't really matter so much. And then our last one, we had our 3/2 gave us a factor of 2x minus 3 with a multiplicity of 3. And then if we wanted to put that in standard form, we would then just multiply that out. I'm probably not doing that with you because that is going to take a very long time to do, especially with that 2x minus 3 cubed. So very rarely are you going to have me having you multiply things out that don't cancel out nicely like the ones we did above. Okay, go ahead, pause the video again and try out number 11, then come back, see how you did. Okay, so for our 1/5 factor, again, multiply both sides by 5, and then subtract out that 1. So next factor was just a -1. I don't have to do anything special to kind of avoid fractions. So my function would be 5x minus 1, but that had a multiplicity of 3. Okay, we have just a 0, or x minus 0, multiplicity of 1, so that's just a plain old x. I'm going to go ahead and put it in parentheses though, and actually let's go back and put this one in parentheses just so it doesn't get confused with a multiplication, even though we don't tend to use that. And then we have an x minus 1, which would show up as an x plus 1, multiplicity of 2. Alrighty, as always, let me know if you have any questions. If not, jump into the practice and start working.